Okay, I want us to look at this problem now. This is kind of an interesting, highly conceptual problem that is definitely worth talking about. In this problem, all the resistors are identical, all the batteries are identical and ideal. Let's say that each of these resistors has some resistance R, and each of the batteries has some EMF E. All right. So we know R, we know E. The question is, there are two questions. First is, where is the lowest potential value in the circuit? The second question is, how many values of potential can we identify? And I want us to actually identify all the values that we're able to in this circuit. So when you're thinking about this in terms of potential as elevation, I want you to consider this circuit. Think about yourself looking at this from an aerial view. So you're looking at the top down view of something that is in three dimensions. So remember those equipotential curves when we were looking at those, and we looked at the topo maps. So those topo maps were a way of representing three dimensions of information in a two-dimensional form, right? As long as you use the curves. So this is a little bit similar to that. If we're looking down on this, we might be looking down at several different elevation levels. Now, the only thing that can change elevation is energy being either supplied to or dissipated from the circuit, right? So remember that when we're talking about potential, we're talking about energy, electric potential energy per unit charge. So it's really energy that we're discussing, and a circuit is, at its core, it's an energy distribution system. That's what an electrical circuit is. It's a very fine-tuned energy distribution system. So for this circuit, all of the wires, anywhere you just see wire, you know that the elevation isn't changing on the wire. Elevation can only change at batteries, where energy is supplied to the circuit, and it can also change at resistors. It only changes at a resistor, though, if that resistor is carrying current. So resistors dissipate energy, but they only do so if you're pushing current through the resistor. Another way of thinking about that is that that resistor heats up only if you're pushing current through it. If I have a resistor that does not have any current through it, just sitting in my hand, that resistor is not dissipating any energy whatsoever. So with the resistor, sometimes you don't know. That's my point. When you first look at a circuit, you don't know if it's dissipating or not. With these batteries, these are all ideal batteries, so we know these are all supplying potential difference. The whole job of a battery is to hold a constant potential difference, so we can feel confident in those. So as far as identifying the lowest point, it might just seem overwhelming first looking at this, but let's just start by doing kind of a mapping exercise with this circuit. If I were to have to guess, like just come out and guess where the lowest elevation in the circuit is, if I look at most of the batteries, most of them are oriented with the positive terminal toward the top of the page. So my first guess at where the lowest elevation would be, a logical guess might be that it's at the bottom of the page. So I'm going to start highlighting down here at the bottom, and all the wires that connect in together. Note that I'm not crossing any components in my highlighting right now. Okay, I'm not crossing any components, just only touching wires. Because if I cross a component, I might be changing elevation. So I'm going to call this, the very first one here, I'm going to call this a reference elevation. And I'll go ahead and label this first reference elevation as 0. Now, is it 0? I don't know, but I have to call it something. So I'm going to say, I think this is the lowest one, and I'm going to call this here 0. Okay, that's going to be my reference 0. Again, that's somewhat arbitrary. If there's a lower value than that, it's not a huge deal. I would just label it negative. That's all. So right away, looking at this first one, I can see this resistor right here has no potential difference across it. I can see that. Just the way that it's wired, just the physical wiring does not allow for any potential difference across that resistor. So I know that that resistor there is not dissipating at all. So if that were a little light bulb or a little LED, it would be dark, right? There's no dissipation happening there. Furthermore, I can do a little bit of analysis in the bottom right-hand corner, but I think right now I'm going to kind of leave that alone and maybe let you think about that a bit, and let's move on. So I'm going to continue on with my highlighting. I need to change color though, because we're going to change elevation. We're going to cross a battery now. Now I don't know what the resistors are doing. I don't know how much current, even if I knew that they were dissipating, I don't know how much current's going through them. So there's no way I'm going to find the potential drop over these resistors. Like, forget it. That's just not going to happen. But the batteries are solid, right? The batteries I know are all E. So if I highlight here, this little piece of the wiring there, what I can know is because this battery here is E, and I know that the long line is positive, right? The short line is negative. I know I'm stepping up E volts here as I go from this kind of yellow color to green. So I know that at this green color, I know here that I'm at E volts. That's the elevation there because I was at what I called 0, and then I went up the stairs from negative to the positive terminal of my battery. And how much should I go up? I know that's E. Again, the whole definition of the battery here is as a potential difference, as a constant potential difference. Okay, so now I have another elevation there mapped out. One of the things that shows me is that these two resistors right here, these two, for instance, those are actually wired in parallel. Those both go from green to yellow. You might not have thought that when you first looked at those two. So kind of cool to see that. All right, switch colors in my highlighter. Let's keep going. Map this circuit out. I'm going to cross another battery. The batteries are my known changes in elevation, so I'm really going to use those, right? I'm going to gravitate toward what I can know. Batteries are handy. So I look at that next elevation there. Notice here that I went through another battery here, right? I climbed through this one from negative to positive, so I went up E again. I went up E, and what that means is that I went green was here at E. I climbed stairs, and the stairs had the height E. So that tells me that here, this level must be 2E there. So that's the purple. Cool. I'm going to keep going. I see that here I can highlight a whole bunch of stuff up here. So I'm going to do that everywhere that's just wire that doesn't cross a component, right? I know that my potential is not changing, so I can label it all the same. So now I'm going to go back and check out the path I took. And so I crossed another battery here. I stepped up another battery. And again, I stepped up from low to high, right? From the negative to positive terminal. The direction matters in a battery. You probably know that from using batteries and things. It matters how you put them in. So I was at 2E, and then I went up E again. So up here, my elevation up here is going to be 3E. Cool. And now other things start to kind of take shape in here as well. We can have a look at that a little bit if you'd like. One of the things that might be interesting is to try to get the rest of the wires, see where some of the other values might be. So if I look at this battery right here, look at that battery. Positive, negative. Now, if I go from blue, I don't want to deal with this resistor that's below it because I don't know the current, whatever. It's just, there are too many things that can be different. But the batteries, again, are really, really well known. So if I start here up at the blue at 3E and I step down through this battery, then I know that I'm at 2E once I've stepped down through the battery because 3E minus E equals 2E. So that tells me that that little piece of wire right there should be purple. That should be at 2E. And what that shows me, furthermore, is that this resistor right here is not dissipating, right? That resistor is not dissipating at all. So if it's not, if that resistor isn't dissipating, then it's the potential isn't changing, And what I can do is just color this all purple through there. Again, that resistor is not, it doesn't have any potential difference across it. So there will be no current going through there. If there's no current going through there, the potential value isn't changing. It doesn't mean the potential value is zero. Doesn't mean that. It means the potential value isn't changing, which means that there's no electric field in there. Okay. So all that stuff that we spent time on, the relationship between potential and E field, that all is applied here in circuits. So we still need all that information. All right. So let's kind of stick with this here. Let's do the same thing. Here's another battery. E, again, we're going to step down as we go from the blue and move our way down the page. We're stepping down, so that needs to be purple here as well. So this is all purple. And purple, remember, is 2E. So I have that mapped out. That tells me a few more things. This resistor here is not dissipating. There's no potential across it at all. And then I have a bunch of other resistors in parallel up in that top row. All right, let's keep going, come down. I see a spot that we haven't really analyzed yet, and that's considering this battery right here. So if I start from the yellow was 0, and notice if I move up the page, I'm stepping down through that battery. So now I need a new color. I'll use this color here. And if I started at 0, which is my yellow, and I stepped down, what that means about that one, starting at 0 and I step down E, the elevation here is negative E. So that's actually my lowest elevation in the circuit right there. And it might have been hard to guess that when I first looked at my circuit. Might not have been able to guess that. I'm going to get rid of some of the stuff down here. I see that since this resistor isn't dissipating, I can just color right through it with this yellow color. And then, oh, there's one more battery, huh? So this guy here, positive, negative. So here I'm starting at yellow and I step up across this battery as I move up the page. So that means, what color does that need to be? That up there will need to be green because that's going to be at elevation E. So I think all the rest, it looks like the rest of our resistors do have some kind of difference in elevation across them, so they will be dissipating. The difference is these down here in the right-hand corner. So now let's look at the right-hand corner. And the question to you is, are these resistors dissipating? So think about it. You can pause the video if you want. The answer is no. They cannot be dissipating, and here's why. If there are two ways they could be dissipating, right? You could say, well, what if, let's do a what if scenario. What if this was at some different elevation there, right? And there are two ways it could be different. One is that it could be higher than 0, and the other is that it could be lower than 0. So let's run through those and see if either of those would make sense. If this brown here was higher than 0, what that would have to mean is that I had current running in, flowing in this direction through all those resistors. And that's not a physical possibility considering conservation of current, because that would be like all this current was magically coming from some sort of unicorn current source at the bottom right hand corner of the circuit, which it can't. Okay, so that's not going to work. The other option is that if that bottom right hand corner is lower than 0, and what would happen if it was lower than 0 is my current would be flowing this way through all my resistors. And again, we have the same problem in that conservation of current, that it would be sort of all the current would be flowing into this bottom corner and just like evaporating, right? it would be just sort of going away, and that's not allowed either. So any amount of current we have going into a junction must be equal to the amount of current going out of the junction, right? We have conservation of current. So what that tells us, what must be true about this corner down here is that actually those resistors aren't dissipating at all. And what's happening is all of this here is all one color and those are at zero. So you might ask yourself, what's the point of those resistors then? Why would those resistors be in there and not doing anything? My answer to you is this happens all the time in circuits because real circuits have switches. It's very, very rare that you'll have an electrical circuit with no switch that simply does only one thing all the time with no ability to control that thing. Usually, that's not something we build a circuit for. So, I'd like you to see this really early on so that you can kind of get used to this. To in some states, if you have a complex circuit, not every resistor in that circuit is always going to be dissipating. You'll see this over and over again. And it's something that you have to really kind of allow yourself time to accept. I still have sometimes students at the end of this course where whenever they see a resistor, there's the assumption in their minds that that resistor has a potential difference, and that's simply not true. So let me just plant that seed now. This is worth doing again, this problem on your own if you haven't worked it, if you just kind of watch the video walkthrough, then go back, look at it, make sure you can label all the values, label all the batteries, all that kind of stuff.